Okay guys, don't panic, don't panic. My voice sounds a little different. It's not your speakers, it's not your ears. I'm just using a different microphone from now on, hoping that you can understand me even better now. Alright, so we do things a little different today in this video, because even before showing you how to implement your anisotropic deep drawing process in Abaqus, I will guide you through some of the things that we will need in order to implement it correctly and actually to get it running. And this is a little different to my other videos, but I thought like it would be very interesting so that you don't have to look at the implementation video over and over again, but that you have some slide that we can refer to and check some information more quickly than having to follow me doing all the steps in Abaqus and explaining the steps in Abaqus. So please first watch this episode and then later switch to the Abaqus implementation so that you understand the steps that we are doing in there. Just for now, you will see some results, some preliminary results. So I set up a quarter-symmetric simulation in Abaqus Standard defining anisotropic material behavior. About the details that would yield these results, I will talk about in the actual implementation video. So first on, how do we define an anisotropy in Abaqus? So we classically define an elastoplastic material model, as you can see here on the left, and in Abaqus we activate the anisotropic material behavior using the sub options radio button that's indicated here, as you can see, and then a little pop-up will pop up literally, and in this one you can specify the 6 capital R values that we've talked about before, and we've actually calculated these for the specific material model. The values that you see here are the ones I used for my simulation, and also you see on the left here that I implemented the flow curve for the material based on the Ludwig's equation using a simple Excel script that would give me the values. However, as you can see here, so check the first 2 values. So going from 0 strain, where initial plastic yielding starts, to 0.05 plastic strain, logarithmic plastic strain, we see the stresses more than double. So between these 2 points, Abaqus will do a linear interpolation. So actually in the first part of these typical material models that are based on Ludwig's equation and similar equations, you should actually refine the first strain interval and maybe do 0.005 or 0.01 steps so that you depict this initial curvature correctly and more precisely than how I did it here. So that's just a side note here. Okay, you see the 6 capital R values, and then you define it according your calculations, and these values you should be familiar with by now since we did it together before. And this is the stuff that you have to define in your material database. And next on, it's okay, how do we connect, or how do we tell Abaqus in which direction is the actual anisotropy defined as the anisotropic behavior, because you see on the left these 6 capital R values can actually define a full 3-dimensional hill yield surface showing or depicting 3-dimensional anisotropic behavior. But since we're dealing with sheets, we usually only use the R22 and R33 and R12 values, as you can see on the left here. So next on, we would check, after we've created our part and in our assembly defined our sheet and meshed it, we will check the element face normal using the query button on top here. Then, okay, now you will see a lot of double red arrows here. The element face normal, and then you click on one of the many faces or one of the many elements that you have in your actual sheet or whatever workpiece that you're dealing with. So if you do this, if you click on one of the element, Abaqus as an output will show you down in the command module the normal components of your face normal vector. And in this case, it is O minus 1, O. And if we look at our global coordinate system as depicted here on the left, I add another red arrow, and you see, okay, the face normal, it makes sense, is pointing in negative y direction. So if we have this element or this element here on the edge, the face normal vector would point exactly in the opposite direction of the green arrow in our global coordinate system. So this is important to remember. So this is what Abaqus thinks that the actual normal direction of our sheet is, and every sheet has a normal direction because it's just technically a 2D object in 3D space. So with that in mind, we move on, and then we have to define our own new user-defined coordinate system. How do we do this? In our part module, we select our sheet, our workpiece, and then click on this radio button, which is create a datum coordinate system, and for our case, defining the anisotropy based on the Hill criterion, we will stick to a rectangular coordinate system similar to the global one we already have. So you select the rectangular coordinate system and then click on continue. And you create this coordinate system in the following way. Since our R11 value, which is our new x-axis of our new user-defined coordinate system, this should coincide or should follow the face normal vector that we've previously talked about. So it was O minus 1, O in this case. So if Abaqus asks you to define your new x-axis, which is the first thing Abaqus will ask you to do, just provide 0, minus 1, 0 in our particular case. Maybe you've created your sheet a little differently and your values might be 1, 0, 0, then it's the same as your global coordinate x-axis, but it could be also some weird type, I don't know, value. But in our case, it's pretty simple. Just type O minus 1, O. But this general rule you should really follow. Next on, Abaqus will ask you to define your YZ plane. So that will correspond to our capital R22, 33, and 12 values. And this is actually the in-plane plane for our sheet. And this is very important because this is the plane where Abaqus actually calculates the anisotropy if you define those three capital R values. So your YZ plane would be your sheet. So usually, since if you use a 3-point approach, there are different approaches to create this datum system. So first you would define your new x-axis, and then you would provide 2 more points or something. Just follow the instructions from Abaqus that really defines your sheet plane and the new normal. And if you do it exactly this way, you will have a perfectly functioning anisotropy according to the actual physics behind the material model that you've previously defined, and you won't see any error. If you do any mistakes here, there might be some error. It might still be calculated correctly. If Abaqus, for example, if you would define O10, so you just do a mistake by 180 degrees, it shouldn't matter much because you didn't define any R11, so it actually doesn't matter if you do it the correct way or the opposite way, as long as your in-plane stays correct. So if you don't do any planar anisotropy but full 3D general anisotropy, you should roughly follow the same approach, and here you just have to follow basically your experiments more than any face normal, because in a 3D element you basically have more than one particular face normal. You can have 6 in total theoretically, and so you should do this approach according to your experiment so that the R11 values, R22, R33 values coincide with the way you have measured your anisotropy. Okay, next on, we assign this new the new user-defined coordinate system to our sheet, to our material, because right now Abaqus still thinks it should do the calculation of the sheet, whatever is going on inside the sheet, according to our global coordinate system. But this is not where we've defined anisotropy. We have defined anisotropy in our new user-defined local coordinate system. So in the tree, you select your sheet, and then under orientation, you assign a new orientation. And you should always define. You can do some crazy shit doing partial anisotropy if you have a sheet that only partially consists out of a material that shows anisotropic behavior, and let's say the middle section would be isotropic. But in our case, we just select the entire sheet and then assign the new material orientation, and we, from the list of new datum system, in my case it was the second one that I've created, but maybe it's just one new coordinate system that you've created. So from the list you choose the corresponding coordinate system that you've previously defined in the way we just talked about. And then, quite important, the normal direction asked in this field here should coincide to your new 1,1 or x direction. So remember, we defined it. That's the actual reason why we've defined this new x-axis to coincide with our element face normal. Because again, if you do it this way and if you do it correctly, you won't get any errors. The physical behavior is correct. I'm just saying, like, you could do a small mistake and still get correct results. However, Abaqus will prompt a couple of warnings that it will change some things automatically, and if Abaqus doesn't change it automatically correctly, then you might see anisotropic behavior that does not correspond to what you see in your experiment. So this is the last thing you have to define, and it's just the way I do it, and it works pretty well. Not showing any errors and giving good results. Okay, so much for the anisotropy definition, and I want to add some more things on interaction properties. If you look at the manual, you see the following quote: every contact pair in the model must refer to a surface interaction definition even if the contact pair uses the default contact property models. What does it mean? It means that once you've defined, let's say, a surface-to-surface interaction between your sheet and your blank holder, you have to specify, I hope you remember this, you have to specify a contact property definition. However, maybe you have used it or tried it before. This contact property definition can be empty, can be entirely empty, and the simulation will still work. Why does it work? Because if you don't specify anything in this list here, Abaqus will use the default values, which is actually indicated in this small tiny node. Nobody ever reads this node. But what does it mean if you don't specify any specific interaction properties? It means that Abaqus by default will use the hard contact interaction property for your normal behavior. It will do frictionless for your tangential behavior. Your discretization method, let's say in the past, was usually node to surface, but nowadays it's defined in your interaction directly. So there, surface to surface is nowadays standard. Back in the days, it could have been also defined in your contact interaction property module. And in NLGeom-on simulation, which is awesome, that's what we always do, you are already activated finite sliding, which nowadays is also more in the, so these two are usually defined nowadays in the interaction modules, but if you work with the input file, then, and if you wouldn't specify anything there, these would be the default properties Abaqus would use for the contact interaction. So try it out. It's a little surprising, and I keep asking myself, okay, why do I have to define a contact interaction property with like an empty sheet of information? I actually don't know. I don't know. Call the support, ask them why you have to do it. Nobody really knows. I just wanted to add this important point. All right. We talked about node to surface versus surface to surface before, but I wanted to come back to this again. And on the left, you see the node to surface, and on the right, the surface to surface result. We are looking from the bottom onto our sheet showing the mesostress. And in cases that, especially since I used a discrete rigid, not an analytical rigid body for our die and our blank holder and our punch, it might be of interest because the surface to surface will definitely smoothen out this fairly coarse contact mesh. However, what I wanted to point out, if your sheet, your actual deformable body, is sufficiently finely meshed, then the results between these two approaches shouldn't deviate much. You can see this if you check the values for the maximum von Mises stress. There is a slight difference, but the overall distribution should be very similar. And if you want to know more about these two aspects, check again my contact and contact interaction video where I talk about the details of the two approaches a little bit more. However, so much for the N2S and S2S approach, but talking about 2D sheet metal forming, what is really important is the following aspect between those two discretization methods. Is when you talk about the shell thickness. Remember, shells are two-dimensional objects in a three-dimensional space. So you always assign, if you don't do it, by default it's 1 unit, let's say usually 1 millimeter in engineering cases, you define a certain thickness to your sheet. And it really matters if during the contact tracking this shell thickness is included or excluded. In our node to surface approach, the shell thickness is always automatically excluded. So it's always on. You see it if you choose node to surface discretization method, automatically exclude shell membrane element thickness is activated. If you choose surface to surface approach, you can choose what to do. If you want to include this or exclude this for your calculation. You might think, okay, what's the advantage? What's the disadvantage? The advantage is that if you include it, your results are much more accurate and physically sound, and as always, it comes at a cost. It's a slightly increased computational time, but let's look at the effect of if we include it or if we do not include it. I've run two simulations. The one on the left, again, is the N2S, where the shell thickness is always automatically excluded, and on the right is the S2S, the surface-to-surface approach, where I've chosen to include, to not exclude the shell thickness. And if we look at the results, you can already get a pretty good feeling why this really matters. On the left, only when the actual two-dimensional object, your sheet, the center of your sheet, in both cases I've defined the mid surface to be the reference for the sheet, you see that the overall deformation of your sheet that you see here looks vastly different to the one on the right, where you have a much higher curvature. This is because here, due to your half sheet thickness preventing the mid surface from coming into contact, your actual deformation behavior looks vastly different from the left to the right. Even though I did not change anything else, it's not the exact time step. Please don't write any comments on this, but I changed a little bit of other things, but it basically refers to the same time point in your simulation. And it also can have effect on all the other things. So it's important to remember that it's more or less a thing of whether you visualize this or not. So in your ODB display options, there is the option to activate or deactivate to render the shell thickness. You should usually use the scale factor of 1 here. And if we activate this for rendering, the same pictures look the following. And as you can see here, my sheet was 0.8 millimeter thick, so my mid surface was at a distance of 0.4 millimeter here and 0.4 millimeter here in contact. Remember the pictures we've seen in the previous slide. And on the left, you see that if you actually render the shell thickness, you see that the blank holder, the punch here and the die here are actually penetrated by 0.4 millimeter in my particular case, because my thickness was 0.8 millimeter. Because the contact algorithm uses this reference plane, our mid surface in this case, for finding the contact. And I hope it's clear to you now that thinking about to include or exclude, or considering the shell thickness or not, is a really important aspect, because it has strong effects on your final geometry, your stresses, your strains, especially because the contact conditions, the point in time when it comes into contact, is really affected by this choice. And this is why usually I recommend to go with surface to surface, especially if you have round geometries, using discrete rigid bodies for your non-deformable parts. You should consider the shell thickness, because in reality, reality also considers the shell thickness. So that's a very important thing I wanted to talk about. Alright, but if you set it up and you click on run, most of the times in those type of simulations, using Abaqus standard, an implicit simulation of such a contact condition, you will definitely see the following. Bam, 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 bam. One does not simply finish implicit simulations without convergence issues. That's an important thing to learn. In the best case, you would stop watching the video right now, try to set your simulation up yourself, and then click on run. And as you can see in the background, these were all the different tries that I actually did, or the different runs. I changed a lot of aspects before moving on to the parts or to the aspects that would actually solve my convergence issues. So keep in mind, implicit simulations, super good. Accurate physics, they always calculate equilibrium conditions in every state. So usually they are used to be compared to analytical formulas or experimental data, or even to verify or even validate explicit simulations, because explicit simulation, you don't have a real equilibrium all the time, so you should analyze the results with care if you look at explicit simulations. So how do you get around the convergence issues and in implicit simulation without affecting the physics of a simulation much? This is what I'm talking about in the next few minutes, and this is a really important topic. Alright, so usually we refer to convergence issues in many cases as stabilization problems, because what the algorithm will try to do is cut the total time, the next time increment, by half, so all your displacements are only half as far, etc., and try to find the equilibrium with boundary conditions adjusted in this case. So what are the measures for you to tackle these convergence issues? For example, I hope you remember this, you can switch to soft contact type. You remember hopefully from the contact video that the hard contact is, from a physical standpoint, the way to do it, because this is how reality works. However, it's numerically challenging, and challenging actually means that it might affect your convergence, that it might pose some stabilization issues to your simulation. So that would be a pretty easy way to maybe get around the convergence issues that you're facing. However, keep in mind that switching to soft contact will introduce some penetration of your bodies, so you will see some overclosure that might be unphysical. So again, numerical stability comes at the cost of, let's say, tweaking the physics a little bit so that your simulation runs. So as always, use it with caution. The next, and I wanted to summarize. So they may resolve numerical problems and contact problems, especially for rigid to deformable bodies, and even more so if your mesh is not very well defined. But we've talked about this in our previous videos, and I think I've also mentioned if you have a very sharp edge, if this is your rigid body and this is your workpiece, such a sharpie object penetrating into your workpiece might be also very challenging for your hard contact definition. So, as we talked about, it may lead to penetration. Okay, next on would be the type of measures that you can define in your step module. So, one thing you can do is switch to an unsymmetric matrix storage. So switch it on, because by default it uses the solver default, and default options here mean that Abaqus, for a friction value below 0.2, which is fairly common in a metal-to-metal surface interaction, especially if you use some sort of lubrication, you will in many cases stay below 0.2. And in these cases, Abaqus standard will use a symmetric storage and solution scheme, even though any type of Coulomb friction causes non-symmetric stiffness matrices. So Abaqus says, okay, for very small friction coefficients, using the symmetric storage approach is computationally cheaper, and so the simulation is faster. And this is actually true. However, the thing is that you might face convergence issues. So if you switch unsymmetric on, your computational time is larger, so your overall simulation takes longer time. However, you will see improved convergence behavior due to a more accurate mathematically depiction of your problem. So there are less assumptions going into this, and this might help improve your situation. And you do it in your edit step module, where you just activate the unsymmetric matrix storage. Next on would be the automatic step stabilization using the specify dissipated energy fraction. What does it mean, and why does it work, and why is deep drawing causing so many problems anyways at the beginning? Nonlinear problems in general can be globally but also locally unstable, and deep drawing, due to a very specific reason, is such a problem. Remember, we talked about the 4 different approaches to define our blank holder modeling, and for the simulations you're seeing here right now, I've chosen a fixed gap for the distance between my blank holder and my die of 1 mm. And my sheet, so my sheet thickness was 0.8 mm. So from the very beginning, at the top, so between the blank holder and the sheet, and between the sheet and the die, there's 0.1 millimeter free vacuum. So this space will cause, and you should hopefully remember this from your forming technology courses, will cause some sort of wrinkling in your flange. You can see this waviness pretty nicely in this picture, and I've shown this waviness again in the picture here on top. And where does it come from? Remember that the way your deep drawing works is that from the left and the right, in circumferential direction in your flange, the material is pushed together. And if you have some space for the material to go, so the 0.12 millimeter above and below the sheet, then you will actually see such a waviness emerging. And this is critical because such a waviness can be referred to, it's very similar to a buckling problem actually. And a buckling problem means that at a very specific point in time, some of the nodes, they change their acceleration almost instantaneously. And this is exactly the point where you will see those convergence issue emerging. So it's at a very early stage of your simulation, your Abaqus standard won't find a pretty solution anymore, because this waviness pattern is caused at a very early stage in your simulation. So in this particular case, and this is the case for many sheet metal forming operations, I know you could also circumvent this using maybe a specially adapted blank holder force approach, so applying a Neumann-Brownick condition so that you don't see this waviness emerging, so that you prevent this buckling problem. But just assume for now this is exactly the way we wanted to simulate, and what are the measures so that we can actually finish our simulation. So in this case, global solution do not work. The manual and many other people will tell you, hell yeah, choose dynamic explicit simulation because it's there. It's easy to use, just go for it, don't worry about it. Be a blind simulation engineer who just uses explicit for no good reason other than it will always converge. Remember, explicit simulations, especially dynamic explicit simulation, it's not about convergence. They don't have convergence issues. They will run and run and run and provide new and new results. It's about stability and physical accuracy. I hope you remember this from our last video. The alternative approaches, and I'm highly recommending going for implicit simulation whenever you can, because you can trust them usually more than the dynamic explicit ones, and they're much faster. If you set up a proper working implicit simulation compared to, let's say, a proper mass scaled etc. explicit simulation, you will still be faster by, I don't know, a factor of 10 to 100, sometimes even more. So the way to do it in implicit problems is to introduce artificial viscous damping energy for these type of analysis. And this is actually what you can also specify in your step module. What are these artificial viscous damping energies? They're actually viscous forces which rely on a certain artificial mass matrix. You don't have to specify a density in order so that Abaqus can actually run this calculation. So it will do an approximation of the mass of your nodes and the nodal velocity vector. We talked about this before. So that when there is a buckling problem, there can be a point in time where there is almost a jump in the vector velocity. And if this is the case, then your damping factor will take care of these jump velocities, because a non-zero damping factor introduces these viscous damping forces, which are then added to your global equilibrium equations. So you treat these local problems, because it's a vector, this force vector only applies to the nodes which cause problems in your overall global system. So that's a pretty neat thing to do. However, think about it. If you add some artificial term to this equation, it's not your true physical equilibrium anymore. We'll come to this later, why keeping this in mind is very important. So in your step definition, it's actually this part down here. You by default here, this is none, and you just switch to specify dissipated energy fraction, and I can tell you that the default values work pretty well in many circumstances, so tweaking them might be a little risky, but you can play around with it, see how it affects your simulation, your internal energies, we'll come to this in a bit, and see how it also affects the physical outcome of your simulation. So much for step stabilization approaches. A third approach is to do a similar thing to your actual contact interaction. And you can, instead of doing it on a global level, you can specify, let's say, similar approaches on a more local contact related aspect. So these buckling problems can also affect nodes which are not in contact right now. But for the contact control stabilization, they usually deal with the problems that occur, especially related to hard contact, normal direction interaction. And these damping terms in your contact controls also contribute to the force and stiffness definition in your contact calculation, not in your global equilibrium calculation. And the Abaqus, as well as I would recommend to use that approach only when all other measures fail to yield convergence or physically accurate results. So in some cases, if you, let's say, only do this here, you might see convergence and get convergence, but the results aren't physical. So in this case, maybe activating your contact control might actually lead to better results. So how do we do it and how do we specify it? So in our to every contact interaction definition, we can add this contact control definition, and there are certain default values. We'll talk about this in a bit, but you can also tweak them. And so from my personal experience, a very small stabilization factor. It's not the actual damping factor. This is usually calculated automatically by Abaqus, and calculating the damping factor itself it's a hard thing to do, and I would say it requires a lot of trial and error going back and forth. So the actual damping factor, you can leave this to Abaqus to calculate it, but you can say Abaqus to scale it down to a certain fraction of it, so 100, so that the artificial energy you introduce is not as high. And usually the normal contact is what causes problem, especially due to this hard contact interaction. And in many cases, the tangent part of your whole contact calculation doesn't cause any problems, even if you activate a non-frictionless model. So scaling the damping factor down to 0 is usually a good thing, so you know that you don't alter the physics of your tangential interaction. And it works with all pressure overclosure types and need to be assigned to the interaction. Remember that all these measures I have presented to you now, this is, I would say, pretty advanced stuff to deal with convergence issues. They affect the accuracy, the physical meaning, the physical outcome of your simulation. But in many cases, they can stabilize the calculations in a sense that you will see convergence, and in some cases it's a little bit similar to your explicit approach, that if you stabilize the simulation, Abaqus can use larger time steps, and though the individual time steps are more costly, the overall simulation itself will be computationally cheaper because you can choose larger time steps. This is very similar to the effect that the ALE approach has on your explicit simulations. Okay, so how do we define these special contact controls? There is in the tree below the interaction properties, there's also contact controls where you can define the factor for the normal interaction and here for the tangential fraction. And you will see a warning here, and if you read it carefully, it says these controls are for advanced users. By now, you should consider yourself an advanced user. I believe in you. If you've come to this point watching all my videos and are not tired by now, you're an advanced user. Using non-default values of these controls may greatly increase the computational time of the analysis, produce inaccurate results, or cause convergence problem. My take on this, well, yes, but actually no. What I found is that using fine-tuned contact controls, the opposite is the case. So the computational time was greatly reduced due to the fact that we just talked about. The results were, from a physical standpoint, much more accurate, and it resolved all my convergence issues that I was facing before. So I think it's just the author of this warning was trying to tell you, if you do apply very unsuited parameters, these things might occur, but if you do it correctly, actually the opposite might be the case. Another funny thing that I found on automatic contact stabilization in the manual, and you should know I'm a huge fan of the Abaqus manual, because it's one of the best manuals for any softwares out there. However, I found the following, that the automatic contact stabilization, quote 1, is not meant to simulate general rigid body dynamics, nor is it meant for contact chattering situation. Quote 2, automatic contact stabilization is used to avoid chattering between the blank and the rigid surfaces, and it is in contact with. In addition, the adaptive automatic stabilization scheme is applied to improve robustness of the static analysis. Hell yeah, okay. So reading the two, I was like, what? My beloved manual? Contradicting itself? What happened? The thing is, it probably depends on how you interpret the importance of the parameters in your contact controls. So the first reaction, I'm totally with Picard here, but I guess it is the Abaqus manual usually tells you just to be cautious, to be careful when using certain advanced techniques in certain situations without thinking about what you're doing. And I'm doing just the same thing. I'm telling you, in many cases, using these measures can help, can improve, can speed up, can render your simulations more accurately, and can resolve further convergence problems. However, keep in mind they come at a cost, and we'll take a look at exactly this right now. So you will see a lot of deep drawing simulations left and right now, and I'm telling you what I've done comparing the two. And for example, in this case, left and right, they both have activated step stabilization and had a frictionless contact interaction with the hard normal contact definition. What I've changed is that on the left, I activated the contact control, and on the right, I did not activate it. So on the right, the both simulations wouldn't face any convergence issues anymore, probably due to the activated step stabilization. So in this case, actually this resolved my convergence problems. But first, I saw this strain distribution. And I was like, okay, I've never seen a deep drawing process where all the plastification takes place at the bottom and none of it takes place in the flange. And most of it should take in the transition of the flange to the wall, and especially there should be a lot of material flow up to this point because it's a frictionless case, so it should be easy for the material to flow downwards, inwards, to the center, to the wall. And then I said, okay, that's an unphysical result. I just activated the step stabilization, but just activating this caused my results to be or to become unphysical. So I additionally activated the contact controls with a certain parameter set and got the results on the left, which looks very good, at least to me. You see the small waviness here, which is also reflected in the waviness of your plastic equivalent strain. And here you can actually see that it's a similar time step, and there is much more material flown inward to the wall, and there is barely any plastification on the bottom. So there are a lot of indicators showing that the left one is much more physically sound than the right one. And this is what I just stated here. Even though on the left my reaction force of the blank holder is higher, this is because due to the waviness my sheet, so to speak, like pushes against our blank holder, which is not shown right here, but this increased blank holder force doesn't really matter, has no effect since it's a frictionless simulation. Okay, so what might have happened on the right? So the picture in the middle now was the simulation only having activated the step stabilization, and if you look at the manual you see the following quote: compare the viscous damping energy that is introduced by activating the step stabilization with the total internal energy and ensure that the ratio does not exceed the dissipated energy fraction or any reasonable amount. The viscous damping energy may be large if structure undergoes a large amount of motion. We can so to speak, say that the latter is not the case. There is not a lot of motion in the body. It's not a huge simulation. There are not a lot of deformable bodies just moving around. It's all related to some type of deformation or contact and so on. So we can say, okay, the latter is not the case. Just look at we will look at the viscous damping energy and the internal energy. I've plotted these two values here on the right, and for the time step we see here, it's indicated the internal energy is the one at the top, so the ALIE is the internal energy, and this is the viscous damping energy. And remember, we've specified we've used our default values where we specified the fraction of the viscous damping energy to be below 0.02%. If you look on the graph on the right, you see that your viscous damping energy exceeds your 0.02% vastly. And this is a very good indicator that your step dissipation, your step stabilization approach causes very unphysical result. So if we just look on the picture to the right, just the graph of internal versus viscous damping energy, an experienced simulation engineer would tell you, I wouldn't trust the physical outcome of your implicit simulation. And then if you would show him the picture on the left, we talked about this before, you say, you have to admit, you're absolutely right, seeing no flow of the material here, having all the plastic strain in the bottom, that is very unphysical for a frictionless simulation. So keep in mind, usually doing all this energy analysis is only something you have to do for your explicit simulations, where you have to check if you increase your punch velocity, if you increase the speed of whatever. If you do some mass scaling using density, then you have to check all the energies and see, okay, how does my kinetic energy relates to my internal energy? It shouldn't exceed a certain fraction. Now, when we do this advanced this advanced stabilization stuff here, we have to do the same thing for implicit simulations as well. And checking your viscous damping energy is the most important thing when you activate step stabilization. Okay, so if the picture on the right is the same as you've seen before from our physically unsound calculation, and the one on the left, where we additionally activated contact controls, you've seen that it seemed to have a positive influence on the value of our step stabilization value, the viscous damping energy, ALLSD, because here you can clearly see it's pretty low, and it stayed well below our 0.02% threshold. And yeah, so the contact controls seem to positively influence the way our step stabilization worked as well. However, once again, using the default values for your step stabilization is usually a good thing. What I've encountered running a couple of deep drawing simulation is that using the default values for your contact control stabilization is actually not a good thing. So again, we're comparing two simulations. The one on the left is the same as we've seen before, but now I'm showing you what parameters I used for the additionally activated contact controls. So again, they both pictures, you see activated step stabilization, frictionless contact interaction using hard contact type, but on the left I've used the adapted values given on the top, and on the right I've used the default values for my contact control stabilization. And using just the default values, not thinking about what I was doing, I got another unphysical sound result where all the strain would concentrate in a single row of elements in our wall. Yeah, I was like, no, that's not correct. What do I do? Because that was the first simulation I tried using the default contact control values, and again, it didn't cause any convergence issues. So the step stabilization resolved my convergence issues, and the contact stabilization with the default values actually improved my computational time even further. But in terms of, instead of getting an unphysical result where all the plastic strain would accumulate in the bottom, which is totally wrong, all my plastic strain now accumulated in a single row of elements in my wall. This is also not a physical result. And I was like, okay, now I have to find a good set of parameters that would still show no convergence problems, but actually would also have a decent computational time and showing physically accurate results. And so I've chosen the parameters on the top, and especially about the tangent fraction and the downscaling of my normal stabilization factor. We talked about this before. And if we further look at the energies of our contact control, you can do this checking the ALLCCSDN value, whereas you have a general energy related to contact stabilization, and you can choose between the one in normal and the one in tangential direction. And since I've used a frictionless simulation, and in my adapted values I used for our tangential fraction 0 as well, we only look at the normal value here. And so this is what you have to check and compare to your internal energy if you activate contact stabilization. So remember, the ALLSD, your general viscous damping energy, is the one you have to check using when you use step stabilization. and if you activate contact stabilization, you should check your CCSD NT or the general form. And as in any case, if you have a non-dynamic regular forming simulation, all these artificial energy terms should be small compared to your total internal energy. And you see between these two values, there's a factor of 60 times. So on the right, where I've used the default values, the artificial contact stabilization related dissipation energy terms were 60 times as much as in the case where I've used the adapted values, and where we actually have seen pretty physically accurate results. And if we now plot the three together, you see the following. On the left, you see the internal energy, looks about right. And then you see the viscous damping, the step stabilization related energy terms, and the contact stabilization related terms, and they're both well below any unphysical threshold, and you can clearly say, okay, the physical meaning of my simulation is unaffected. I can still trust the outcome of the internal energy related strains and stresses and so on. Opposed to that was the simulation on the right, the one where all the energy concentrated in the single element row in the wall. So there was physical BS. And you see that the step stabilization energy was even higher than the internal energy, even though it was supposed to stay below a fraction of 0.02% of the internal energy. And as well, the contact dissipation energy was also, the fraction is like 25% of my internal energy, also way too high. So you see that if you activate both step stabilization and contact stabilization, they can positively and negatively influence each other. Remember, positively in the sense that once you've chosen correct values, it can make your unphysical simulation where you only activated step stabilization yield physical accurate results. However, if they negatively amplify their negative effects, it can get out of control. And this is the reason why Abaqus actually prompts a warning where it says contact stabilization and automatic step stabilization should not be used together in the same step, since it may lead to excessive damping or convergence issues. And the excessive damping is the one you see here on the right, when they negatively amplify each other because you've chosen non-optimal parameters, then it's total BS what you get as a result. However, on the left, you see a pretty fine-tuned simulation, again, where I activated contact and automatic step stabilization, and I had zero convergence issue. It was a very fast simulation, and the results were pretty nice and accurate, but only once I've changed the values for the contact controls. And so I can recommend to sometimes actually use both. Remember, this is what I did in previous slides, and this is what actually got me to the point where I had a fast and physically sound simulations without any convergence issue. But one last thing I want to say is that in general, any sort of artificial energy in implicit simulation causes the results in each step to deviate from the physically correct equilibrium results that implicit simulations are usually known for to produce. So if you introduce those artificial energy terms like we've seen here, like contact and step stabilization, you should really make sure that you check the amount of those energy terms. This is what we've done. This is what I've shown you here in relation to your total internal energy. And the important thing is, the higher the portion of these terms is related to your internal energy, the higher the physical deviation from the actual physically correct solution is. So using implicit simulation as a verification, let's say for explicit simulations, is no longer a good idea once these artificial energies exceed a certain fraction. So however, and this is what you've seen on the left here, if these terms are negligibly small and still do their job, meaning that using them you actually reach convergence and you don't face any other numerical issues anymore, then the computational time to obtain the results is vastly less than if you've chosen dynamic explicit simulation. That would have been the alternative, and we will also later talk about this. So remember, it's the same as in explicit simulation. There, any sort of measure to speed up the calculation time, like mass or speed scaling, also introduce like these artificial energy to your system, which will usually speed up your simulation, because it's not a problem about convergence in the explicit case, but usually about calculation time. So your artificial energies will solve the problem of a long computational time, but they will affect your physical results. And for some reason, explicit simulations are more, I'd say, en vogue today, because they're simple to use, easy to set up. You just click on run. Your simulation will run to the end and show you some nice, colorful pictures. And that's the reason why they're mainly used so often today. And even, especially in complex contact forming operations and so on, they're usually one of the preferred options today. But the computational time is the remaining drawback, especially, and this is an important factor to consider, implicit simulations can be, using multi-core simulations, can be easily split up so that you can do a very nice parallelization of your problem. So if you have large problems, using many cores is a very good idea in implicit simulation. In explicit simulation, you can't do the same mathematical approach to parallelization as you can do in implicit case. So even modern computers having all these fancy hundreds of cores, it doesn't bring much in explicit simulation actually, because the mathematics and the physics prevent you from using a super nice parallelization approach. So with the computers getting faster and faster, but mainly due to many cores being available, not a faster clock speed of your CPU, the long computational time of your explicit simulation remain a critical issue, so to speak, and a critical drawback of this approach. And this is the main reason why I definitely recommend to always consider implicit simulation, and especially since if all the artificial energy terms stay below a certain value, you can really trust those results and use them for validation purposes of your other explicit simulations, and also as a validation or comparison to your experiments and analytical formulas. So enough of talking. Let's dive into Abaqus and set up our deep drawing simulation. See you there.